Hello everybody. Today we are looking at a branch of physics known as waves. Without much time wasting, let us dive into this topic. What is wave? Wave is a very broad concept in physics, but we start with a simple definition. A wave is a disturbance that travels from one point to another in a medium, transferring energy in the process without causing any permanent displacement of the particles of that medium. Otherwise, you can also say a wave is a disturbance that travels through a medium, transporting energy from one point to another along as it travels, without causing any change in the medium in itself. That is wave. There are two kinds of wave by classification. We have wave by medium classification and wave also by direction on classification. By medium, we mean how the wave travels in a given space. Now, under medium classification, we have those waves that require material medium for their propagation, and they are called mechanical waves. We also have those waves that do not require material medium for their propagation. They are called electromagnetic waves. Please note, by material medium, we mean matter such as solid, liquid, and gas. So certainly, some waves need matter before they can be propagated in space or before they can travel. These waves, as said earlier, they are known as mechanical waves. While those that do not need matter, I repeat, they are called electromagnetic waves or light waves. Examples of electromagnetic waves, as you can see there, are visible and invisible light. Visible light include all the colors of light you can find in the spectrum of white light, while invisible light include those lights that we cannot see, and these are infrared, radio waves, ultraviolet radiation, X-ray, gamma radiation are invisible light. So, mechanical waves, again, is of two types. The two types of mechanical waves are longitudinal and transverse waves. Longitudinal waves are those waves that travel such that their direction of travel is perpendicular. Longitudinal waves, transverse waves rather, are waves that travel such that their direction of travel is perpendicular to the direction of vibration. This is direction of travel, the x-axis, which is propagation, while this is the y-axis, the vertical axis, which is the direction of vibration. Now this curve, like a sine curve, shows the direction or pattern of the wave as it travels along from left to right. The particles of the medium vibrate vertically in this fashion, while the wave travel along horizontally in this fashion. So eventually it gives this curve pattern. Sorry about the H. It gives this curve pattern. Now we have the other type of mechanical wave known as longitudinal wave. Longitudinal waves are waves that travel such that the direction of vibration is parallel to the direction of travel. A typical example of longitudinal wave is sound waves. As you can see, this is a representation of longitudinal waves. As the wave travels from left to right, it consists of regions of densely sparse lines and regions of concentrated lines. These lines are highly spaced, widely spaced, and this one's concentrated lines or high density lines. Now, this is how the wave travels. For instance, sound wave, from its source, the first layer of air is expanded as the sound proceeds from the source, and the next layer of air after that one is compressed, and that would eventually leave that compressed layer on expansion to expand the next layer of air, and therefore the expanded layer of air again the second time will cause a compression rather, and so forth. The alternating sequence of expansion and compression continues until the wave gets to its destination, or reaches its destination rather. Now, the expanded regions you can see are known as a red fashion arrow, while the compressed region is represented by C. Here we have dense lines, and so this sequence of R and C in alternating fashion or manner will result in movement of the particle of the wave. So here we have the diagram. We are not done yet. Pardon for that each. Now you can see in the diagram that we have a point A at the top of the waveform, another point G, and another point L. These 3 points labeled are known as the crest, top point on the waveform. There's a fourth point that is not labeled, but also known as a crest. Now, by position. Underneath, we have the lowest point on the waveform. Below this point is called the trough. I is trough also. Likewise, T. Here, the wave starts from this point, and this point is called the origin. Here, the wave is being generated from the origin of the wave. O is the point known as the origin of the wave. We can also see it as the 0 point or 0 mark. At this point, the displacement is 0 and the time is 0. So at this point, we switch on time and assume that the particle of the wave starts motion under vibration. So what happens? As wave travel from O, it goes in the positive direction. That is, the wave particle continues to increase in vibration. So the vertical axis Y represents the displacement from its main position. So what is the main position? The line O through F prime through K prime to Q is the S axis, and it continues. That line is the rest position also known as the equilibrium position, also known as the mean position. This line will help us to understand the other concept that we have seen before, that is amplitude, circle, wavelength, frequency, and slope. Therefore, we must note that the x-axis is the mean position. So when I use these words interchangeably, don't get confused. I'll sometimes say mean position, equilibrium position, or rest, better still, rest position. So a particle on this level is at rest on the x line. So it's at rest. So the particle is undisturbed because it has no displacement from this horizontal rest position. So when the particle is disturbed, it will now have a vertical displacement such as this point. Every other point on this curve represents the displacement, and then represent the position of the particle from the rest position. So therefore, there is a distance of a particle at this point from the rest position. That distance is called displacement. And the maximum displacement ever you can find in a wave curve or wave diagram is the displacement from the crest, which is the highest point, to the mean position. That displacement is called the amplitude of the wave. As seen before in the definition, the amplitude is the maximum displacement from the equilibrium position. We have already seen that this line represents the equilibrium position or the rest position. We can also see the maximum displacement of the wave as the maximum distance from the trough to the equilibrium position. So from point D to the equilibrium position is also an amplitude, because the absolute value of the distance from D to this position or this point is equal to the distance from A, the crest, to this point on the rest position or rest frame. Take note of that. So on that maximum displacement or distance is called the amplitude of the wave. It is a very important property that we need. The next concept there to be considered is the circle. The circle, what is a circle? A circle is a complete to and fro movement. So if the wave starts from O and goes round and returns to the level where it started from, and that's half a circle, and turns round and returns to the circle once again, that's a complete circle. So with the idea of circle, we say a circle is a complete to and fro. I know somebody wants to ask me, why is the move from O to A and down to this point not a to and fro? After all, the particle has returned. Yes. The concept of phase will help us to understand why, although the particle is at the rest position at this point and also at the rest position in the beginning as well, but yet we cannot say that it's a complete to and fro. This is a to. From O to this point through A is a to, and the fro is the return from that same point back to S prime. And why is this so? The reason is not far-fetched. Phase has the answer. So let us see what phase means. In the wavefront, you notice that point B and point point F, and even point H and K, they are all having equal distances from the rest position. But point B has the wave traveling downwards, the particle of the wave traveling downwards. Point F has a particle or points of the wave traveling upward, and point H also has the points of the particle of the wave traveling downward. So therefore, B and H correspond in the sense that the direction of travel is the same, and not just that, they have equal distance from the mean or equilibrium position. It therefore means that point B and point H are exactly alike, and so we say that they are in phase. They are in phase because the particles of the wave at point B and H, they are moving in the same direction, that is downward direction, and also have equal distance or displacement from the equilibrium position. As you can see, the distance from H to this point, the equilibrium position, is the same with the distance from B to this point, the equilibrium position, and they are traveling in the same direction. But as of F has the same distance, but F is traveling in the opposite direction, that is in the opposing direction of the wave, and so F is not exactly in phase, it's not in phase with B and H. So after B, the next point that we notice that has the same direction, exactly the same direction and the same distance, is H. Therefore, we say that B and H are two successive points in phase. Please take note, successive points in phase. If we move on, there is another point, all right, not which ought to be N, N at this point has equal displacement as K and H and B and F, but at N the wave is actually traveling down. So B, H and N therefore correspond to what? Points on the wave that are points on the wave that have equal displacement from the mean position and also traveling in the same direction. It therefore means that B, H, and M, that's M, they are in phase, but B and H are two successive points in phase. H and M, they are two successive points in phase. B and M, they are not successive, because before you get to M, you must first reach what? K. So before you get to M, you must first reach H from D. So B and H are successive points in phase. H and M, they are successive points in phase. So that we now say that B, H, M are in phase, but B and H are successive. H and M are successive points in phase. Similarly, F and K are in phase, because F and K, they are traveling, the particles of the wave at F and also at K have equal distances from the equilibrium position, and at the same time they are traveling upward in the upward direction. It therefore implies that F and K are in phase. Okay, F and K, they are in phase. So therefore it means that 2 points on the wavefront traveling in the same direction, having equal distances or displacement from the equilibrium position, describes phase. So that will take us to the initial concept of a circle that we try to explain. So at that point we said that O and this point here, they are not, it's not a complete to and fro. A complete to and fro involves 2 points in phase. At O, the particle of the wave is rising. At B, the particle of the wave is falling. The wave is going down. Okay, note at O, the particle is rising. At B, so at this point, the particle is falling. Although the two of them are exactly on the equilibrium position, this point and O. But just that the wave is falling here and the wave is rising at O. So they are not in phase. So from O to this point, it's just half a circle. They have equal displacement, that is zero displacement from the equilibrium position, but they are traveling in opposite direction. But when you get to F prime, you notice that F prime is the next successive point after O, such that the particle is rising, that means traveling in the upward direction, and also having the same distance from the equilibrium position. In fact, they are exactly on the equilibrium position. F prime is on the equilibrium position. Likewise, O is also on the equilibrium position. Therefore, O and F prime, they are exactly in phase from our last explanation. That tells us that O and F prime represent one phase, and that means one circle. So two successive points in phase means that the phase gap between them is one phase or one circle. So take note, one circle here is regarded as a phase angle of 360 degrees, which is also the same as 2 pi. So in this study, we prefer to use pi. So we have an angular change from O to F as 2 pi phase angle. Now, we have seen that O and F prime, they are in phase. Therefore, it means this point will also be in phase with this point, because at those 2 points not labeled, the wave is actually coming down. And so we can say also C and this point here not labeled, they are in phase. And we can say E labeled, this point labeled E, and this point labeled J, they are in phase. Why? Because at J, the distance to the equilibrium position is the same as the distance at E to the equilibrium position. But just that they are both traveling in the same direction, that makes them to be in phase. And in addition, they are two successive points, E and J, because after E, the next point when you have the wave traveling in the same direction and having equal displacement is J. So E and J are in phase. So that means that this point and O will therefore be in phase. So that C and this point are in phase, and also C and O are in phase. C and O are in phase, but they are not successive, because before you get to O, there's another point not labeled, this one, so that is closer to O or closer to C than the two of them, C and O. So this point is closer to C than O. So this point is a successive point in phase with C, and also a successive point in phase with what? O. C and O, they are in phase actually, but mind you, they are not successive, because in between them there is a point between them that is successive, that is in phase with the two of them. So that explains that. In the same vein, we can therefore say that the points A and G and L, they are all in phase, because they are all crest. So the peaks are in phases, the troughs are in phases, but D and I are successive points in phase, I and P are successive points in phase. And recall that we said the angle between two successive points in phase is 360, which is also called 2 pi in terms of radian measurement. So therefore, A and G therefore are in phase with a phase angle or phase difference of 2 pi, and they are successive points. G and L, they are two successive points, and with a phase angle of 2 pi likewise. So therefore, the phase angle between A and L will be what? 4 pi, because from A to G is 2 pi, from G to L is another 2 pi. So if we are to move from A to L, we are going to make a total circle of what? One circle which is 2 pi, another circle which is another 2 pi, total of 4 pi. Now, another beautiful concept is the wavelength. From the concept of circle, we have seen that two successive points in phase has one circle between them. We have also seen that the angle in one circle is 360, which is 2 pi. So 2 points in phase have angle of 360 or 2 pi between them. Then from that description, we can now describe another phenomenon or concept called the wavelength. The wavelength means the horizontal distance between two successive points in phase, or two successive crests or troughs. Therefore, from that definition of wavelength, it means that A and G, they are in phase, and so the horizontal distance between A and G is one wavelength. Just like point O and point F, look at the arrow, use the arrow to trace it. F prime and O, the horizontal distance between O, the origin, and F prime, as the cursor moves, take note. F-O, F prime, this point. The horizontal distance is exactly one circle. If we do the counting, half a circle, one circle. So two successive points in phase, or two points which have one circle between them, the horizontal distance between them is called the wavelength. So this concept they come here. The wavelength describes two successive points in phase in terms of the horizontal distance along the earth axis, while the circle talks about two successive points in phase having a phase angle of 2 pi, and 2 points in phase are points traveling in the same direction and having equal distances from the mean position. So if we must recap this, therefore we can say that B and H, as they are in phase, the distance between B and H is one wavelength, and the distance between H and this point M is another wavelength, so that the total distance between B and M is 2 wavelengths. Alright, the distance between A and L, therefore the crest and the A and the crest L will be 2 wavelengths. So therefore the distance between A and B will be what? Let's count. That will be from A down to this point, a quarter wavelength half, because from O to A is half of half a circle, and from A to this point is half of half a circle. That implies that OA is quarter wavelength horizontally. A to this point is another quarter. That's quarter plus quarter, that's half, and to this point D, another quarter. That means the distance between A to this point and down to D will be a quarter wavelength plus a quarter wavelength. That means half a wavelength. So the distance between point A and point B is half a wavelength, and half a wavelength represents half a circle. Of course, one circle gives rise to one wavelength horizontal distance, so half a circle will give rise to half wavelength. And the distance between horizontal distance between D and say this point here will be, or let's say the horizontal distance between D and K prime. So from here, this is D on the x-axis, exactly D. So from this point D to this point F prime, that will be a quarter wavelength. From F to this point, that will be half a wavelength, and from this point to K, another half a wavelength, K prime rather. So K prime plus this point, half a wavelength, plus another half a wavelength to F prime, and then to the middle, another quarter. So half plus quarter, that gives 1 quarter. So from D therefore to K prime, the horizontal distance is 1 quarter wavelength. That means 1 1/4 wavelength. So please, in other examples, you'll be asked to determine wavelengths between 2 points along the x-axis. So the x distance, x can be counted in terms of what? Wavelength. And the unit of wavelength generally is either in centimeters or meters or other metric units of distances. Please take note of that. Also, the vertical displacement y is also in distance, and it's measured in meters likewise, or any other metric unit. Take note, this horizontal distance represents both the time axis. This horizontal axis called the rest position represents 2 things: the time axis and also the horizontal distance traveled by a wave. Very interesting. Please, as a learner, you need to observe carefully this diagram, because it is the key towards understanding the concept of waves. I want to talk on the last one, which is periods. Using this diagram, I will not stress much on frequency. Just like we know that two successive points which are in phase have one circle between them, and the horizontal distance between two successive points in phase is 1 wavelength, that will give rise to another concept. We're also related to them, or rather related to them, the period, that's time. As we move from left to right, beginning from the origin, time elapses, and so The time taken for the wave to make one complete circle, that time is called the period. So if we divide the total time by the number of circles, that gives us the period. So the time taken for a particle of the wave to travel from O down through A and down through D and then return back to the same level as O where it started with, which is level F. That time is called the period. As you can see, level F prime rather is exactly in phase with O. So FO and F prime, which are two successive points on the waveform that are in phase, representing one circle. The time taken for a particle to move, therefore move from O to F prime, is called the period of the wave. So it's likewise manner, you can say that the time taken for a particle to travel from G to L is the period. The time taken from that same particle or another particle to travel from A to G is the period. You can in that same fashion say that the time taken for a particle to travel from D to level I is the period, and level I to P is also a period. So any two successive points in phase, the time taken for a particle of the wave to travel between those two successive points is the period. Just like the distance between these successive points is the wavelength, the horizontal distance I mean. So take note of that. So from O to K to F prime is one period. From F prime to K prime, another one period. That's two periods from O to K prime. And from K prime to Q, another one period. It therefore means that from O to Q we take exactly 3 periods. And that means the distance from O to Q is 3 what? Wavelength in terms of horizontal distance. Let's do the count. Then from here to here is half, another half, that's 1 wavelength, half, another half, that's 2 wavelengths, half, another half, that's 3 wavelengths, which means 3 circles, and that also means what? 3 periods. 3 wavelengths, 3 periods, 3 circles between what? O and Q. That means O and Q are exactly in phase, but they are not successive, because if you take every periods to get to Q, which is an equivalent of what? An horizontal distance of 3 wavelengths. So much has been put into this diagram. It's now time for us to turn our attention to the next concept, which is the wave speed. Here we are, the wave speed. The wave speed is describing how fast the wave moves from the origin O that we saw in the last diagram, previous diagram, along the x-axis or the time axis, and therefore the distance covered as the wave travels from the origin is x. Please take note. The distance is not in the vertical direction. The wave is traveling from O down across to the left, as from the right, the origin to the left in the diagram, but it's vibrating in the vertical direction. All right. So the speed of the wave depends on how fast the wave travel along the x-axis with respect to time. So from the original definition of speed, we know that speed is a rate of change of distance with respect to time. So since the wave has properties such as time and distance along, then we can say that the speed is the distance, the ratio of the distance, to that of the time. So if the wave covers x distance in time t, the wave speed is therefore x over t. Suppose that this x distance is measured in wavelength. Let's assume that the wave covers an horizontal distance x that is equal to 1 wavelength. And in doing that, we already know that the time it will take a wave to cover a distance that is 1 wavelength, that time is the period, capital letter T. So therefore, the wave speed therefore means that if a particle has a distance of x, and that x is 1 wavelength, so we put 1 wavelength here, and that time that the particle that we fish the particle will cover that distance of 1 wavelength, that time will definitely be the period. So replace T with capital letter T. So the wave speed therefore is lambda over capital letter T, period. Lambda over period. Lambda is the Greek word for wavelength. So take note of that, and then From the old definition, we know that wavelength, we know that period of a wave is given as t equal to small t, the time taken to complete n numbers of circles. From the study of harmonic oscillation, we have seen this before. The time taken to cover number of circles, and frequency also is defined as the number of circles divided by time. So if we return and then substitute this here, we have a different formula. We now have a formula quite different. We have, if we go and substitute f in place of 1 over t, then this formula becomes lambda f, which is a very important equation here in physics, not okay. So that's the wave. These are the waves. This represents the wave speed, and the other one lambda f when we use frequency instead of period. So the student is allowed to derive or deduce that by replacing this 1 over t found here with f, and that will leave us with f lambda. So the student is allowed to show that. Let's take a simple example. A difference between successive points in phase on a progressive wave is 5 meters, 5 centimeters, beg your pardon. If the speed of the wave is 0.2 meters per second, calculate its period. Solution: V is equal to 0.2 meters according to the question. The wavelength is 5 centimeters. Please, in terms of metric units, two quantities must be the same. The unit here is meters for the speed, and therefore the unit for the wavelength or distance here must also be in meters. So we have to convert this. Either we change this to meters, or we change the meters here to centimeters. The metric unit must be the same form. So therefore, we know the wavelength according to the question in meters. They say we should calculate the period of the wave. So of course you know what period is, the time taken to make one circle. So we now define this equation, quote this equation that we have seen before, and substitute the respective values. Speed is 0.2, we put that in place of in this formula. Take lambda and replace that lambda with 0.05 rather, and then make this subject of formula. If we cross multiply, the student should show that and make t the subject of formula. We arrive at this expression, and then when we get to that point, we will get the final answer. Please, as a student listening to this or watching this, you must note, have a material beside you where you can actually confirm every idea being given to you at a point in time. So it is important, imperative for the student to show how we arrive at this value by cross multiplying and then dividing both sides by 0.2 or simply making t subject formula. Thank you for listening to this example. We shall proceed. Now, a very beautiful concept is the wave equation. We have described the wave speed, which talked about the distance covered, the rate at which distance is covered by the wave as the wave travel along the x-axis. Very well then. So what about the vertical displacement? What describes it? And that is here we are. That one is described by what we call the wave equation. Now, the wave equation represents the vertical displacement, which is y. And there we have the A. A is the amplitude that we saw the other time as the maximum vertical displacement. So the displacement at any time, at any point on the wave form is given by A sine, open bracket, omega t minus kx. Omega is not a new word here. Omega is an angular quantity which tells us the rate of change of angle with respect to time. As a student of physics, you must have come across this symbol, omega, which describes circular speed. And this quantity, omega c, is an angular quantity, okay? Because omega describes angular speed, so the rate of change of angle with time. And here, c is time, k is angular wave number, a new concept, and S is the S here represents the horizontal distance as the wave travels. Please take note, this value Ks is known as the phase of the wave. It is with this phase that the wave advances, actually travels along the path as it goes. So take note of this formula. If the wave is traveling from left to right, minus is there, and from right to left, plus is between the two angular quantities, omega t and ks. Here we define ks as 2 pi over lambda wavelength. Where lambda here is the wavelength, like as we have seen before, and also this omega is defined as angle over time. Therefore, if a wave has covered an angle of 360, that is 2 pi, which represents 1 second, the time to do that is what? The period. So we now change the angle inside in the original formula that we have seen before to 2 pi in previous class, and then we change the time to t. Okay, and that will give us 2 pi over t. But recall that 1 over t is f, so we cannot as well write this formula as 2 pi f. The student should show that this can result to this, basically because f is equal to 1 over t, or t is equal to 1 over f. So more importantly rather, equation 1 and 2 are of interest to us. If we substitute the quantities of omega and k into the expression, equation 1 and 2, equation 1 becomes 2 pi ft minus 2 pi x over lambda, and then it becomes, if we have to factor out the quantities of 2 and pi outside the bracket, we have an expression like this: 2 pi bracket ft minus x over lambda. Similarly, if we replace the omega with 2 pi over t instead of 2 pi f, then we shall have an expression like this: 2 pi t over capital T, which is the period, and we also have 2 pi over 2 pi x over lambda, and do the same thing that we did previously by factoring out 2 pi. We shall have another expression, t over capital T. The difference between both expressions is that here we have ft and here we have t over what? T. That's just the difference. Here is x over lambda, x over lambda. So where a as before still remains the amplitude of the wave. So equation 3, this is equation 3, and equation 4, they are important equations to determine the vertical displacement of the wave. And this description of the vertical displacement is what we call the wave equation. So equation 1, 2, 3, and 4 are known as the wave equation. All right, now we are here. There's an example of wave equation. The wave equation here. The frequency of a vibrating source. All right, this is an example for waves. Wave travel, not really displacement. The frequency of a vibrating source is 450.0 Hz, and the velocity of the sound it produced is 330.0 meters. Find how far the sound travels when the source completes 50 vibration. I think this ought not to be here, this line. So we have frequency f equal to 450 Hz. The unit of frequency is the Hz, and then we have v is equal to 330 meters per second. That's the speed of the wave. We have the time, and from the fact that f is equal to n over t, we say, since f is equal to n over t, we can say t is equal to n over f, making t subject of formula. If we cross multiply and divide by f, we arrive at this.
If we go and substitute now the value of t, which is n over f, here in place of this t, we shall have n over f. And then when we finally simplify, we have x over xf over n, and substitute the corresponding values for f and n, 450 and 50 in their respective positions, and replace the v with 330. Then make s subject of what formula. So then to confirm this, that will result to s equal to 36.6 meters as the wave distance traveled. Here we are looking at some of the properties of waves, reflection of waves. Now, in this study, you can see that the wave here has some properties that need to be considered. The properties of wave are 5. First one is reflection, as you can see on screen. The second one is refraction. The third one is interference. The fifth one is diffraction. The sixth one is reflection, second refraction, third interference, fourth diffraction, and fifth polarization of wave. Now, the first 4 properties are common to all waves, whether transverse or longitudinal waves, but take note, the fifth one is particular to only transverse waves. Polarization, only transverse waves can be polarized. I'll get a full light on it. So now let's look at this first property, reflection of wave. Consider a wave traveling from a region. On reaching a surface, the wave bounces back. So reflection actually is the throwing back of a wave when it encounters a barrier on its path, or the bouncing back of a wave when it meets or encounters a barrier in its path. So an advancing wave encounters a barrier, will be thrown back. But the way the wave will return depends on the angle that the wave makes with the surface that causes the bouncing back or the reversal. So if the wave travels such that the incident direction is exactly at right angle, that is direction of travel is right angle to the interface causing the return, that wave will return along the same path. So ON represents a wave traveling from this region and striking this surface. So ON, the line ON is the incident direction. Please take note, this line is not showing the wave front, it's just showing the direction. Take note. Could be plane wave, could be spherical wave. On striking the surface, the wave return in the same direction ON, because ON is at right angle to the surface. So we say ON is normal to the surface. That's the correct one to use. Then, if the wave now travel at an angle different from 90 degrees to the surface, then we cannot describe that angle with respect to the normal. Now, the wave, consider a wave traveling along PO and it strikes the surface at O. Look at this arrow now, showing the indicating direction of the wave. As the wave gets to O, it bounces back, but this time not back along the path OP in the reverse order. Rather, it takes a different direction in the same medium, and that direction is OQ. So OQ is the reflected wave, or the returned or reversed wave as a result of the incident wave OP. So we call this wave that was reflected, that became reflected, or rather that was reflected at the boundary interface as the incident wave. And the angle that this wave makes with the normal direction is called the angle of incidence, while the angle that the reflected wave produced as a result of this incident wave being bounced or returned, that angle the reflected wave produced we make with the normal is called the angle of reflection. Angle of reflection. And according to the law of reflection, we're told that the incident wave, the reflected wave, and the normal all lie in normal. Now the normal wave all lie in one plane. They are all in one plane. So at the normal at the point of incidence, take note. The second law states that the angle of incidence, that is the angle which the incident wave made with the normal direction, is equal to the angle the reflected wave made with the normal direction. So angle I is equal to angle R under the reflection of wave. I think it's good. So far we have seen the properties of wave, the first property of wave rather, which is reflection of wave, and we know. Please take notes, not shown here, there are different types of reflection of wave. We have diffuse reflection, and we also have regular reflection. In diffuse reflection, the reflected waves are scattered after reflection, and so that the reflected waves travel in direction not parallel to themselves. But if we have a sequence of reflected waves parallel to themselves after reflection, those waves are regular reflected waves. And for this to happen, it means that the reflecting surface must be a smooth surface for regular reflection to happen. So most objects that you can see on a screen, or as a result of reflection, as a result of their images, as you can see on the screen, as they are caused by regular reflection. Diffuse reflection tends to scatter the rays, and so very difficult to observe images of this object under diffuse reflection caused by a raw surface. That is why you can see yourself standing on a mirror, or you can see your image clearly, or on a polished wood surface, or you can see your image, but on a rough sandy surface, you hardly see your image there, because the reflection from that raw surface is scattered or diffused. So another word for diffuse reflection is scattered reflection. Another word for regular reflection we'll say smooth. Now, this reflection, regular reflection, is as a result of smooth surface, highly polished surface, while diffuse or scattered reflection is as a result of reflection emanating from rough surfaces. Please take note of that. So we move from reflection to the next. Here comes refraction, the concept after reflection. When a wave travels in one direction and that wave incidents on a boundary surface separating two media, that wave, sometimes if the wave is able to go through, the direction of that wave will change. Look at the wave, an incident wave PO. O is the boundary surface between two media, media 1 and 2. The medium 1 could be air, and medium 2 could be water. Since light could be air, and medium 2 could be water. It could be that light wave is traveling from air through water. It could also be water wave traveling from deep water, which means medium 1 could be deep water, this area now, while medium 2 could be representing shallow water. As the wave moves from deep water to shallow water, or from air to glass, or air to water, the boundary interface between air and water, or shallow water and deep water, is this interface, this white layer you can see, and this layer separates the two regions, or the two mediums. So therefore, this layer tells us that one medium has a higher density than the other one. So as a result of that, it implies that when the wave travel from the first medium into the second medium, the wave direction will change, or the course of the wave will change. Look at the wave. If we are to continue this line OP in the second region, which that is region 2 or medium 2, the line is supposed to go directly. By normal intuition, look at the line. If we continue, this is the direction. But rather, it bends away towards the normal. It therefore means that the wave has changed its course. So refraction can be seen as a change in the direction, wavelength, and speed of a wave as it crosses the boundary interface, or the boundary between two surfaces of different densities. So when a wave crosses the boundary face or boundary surface of two medias of different densities, the wave direction changes. Likewise, the wave speed. In fact, it is the change in wave speed that will actually result to the change in wave direction in the second media. And take note of that, the wavelength of the wave also changes. So in refraction of wave, we have the change in direction of the wave, change in wave speed, and also change in wavelength of this wave. So take note of that. Now the wave is traveling from a dense medium to a less dense medium, and the surface separating the two mediums is known as the plane boundary, or the boundary interface between both media. So the angle which the incident wave make with the normal direction is called the angle of incidence. Take note, and just like in reflection of wave, any wave traveling perpendicular to the boundary surface will go through the boundary surface undeviated. So that wave is called the normal, just like we have under reflection. So this wave can travel straight without refraction and without bending. But this one, because it makes an angle with a normal wave, that angle, which is known as the incidence angle, will change as the wave crosses the boundary interface. So refraction happens when a traveling wave, that is an advancing wave, makes an angle I with the normal to the surface at the plane boundary. So take note of this simple concept. So this wave here is actually this one, but now it has changed its course. So we say that the wave OP has been refracted to become the wave OQ. And the angle between the refracted wave and the normal now, the normal continues straight along through the two media. The angle between the refracted wave and the normal is called RR, which is angle of refraction. Please do not confuse angle of refraction with angle of reflection, as students often do. So please take note of that. Refracted angle is the angle between the refracted wave and the normal. While the angle of incidence here is the angle between the incident wave and the normal. So take note of that too. So having said refraction is a property of wave that emerge when a surface when a wave tends to cross the boundary phase between two surfaces of different densities, then they will move to a very important property of refraction of wave. But we must note, if the wave is traveling such that medium 2 is denser than medium 1, you see that the refracted wave bends towards the normal. So assuming the wave was actually coming from medium 2 into medium 1, it means that the wave bends away. So if OQ was the original direction of the wave, which is the incident direction, the wave will bend. Refractive index N of a pair of media is a property of refraction. So we can now determine the ratio of the speed of the wave in medium 1 to the ratio to that of the speed of the wave in medium 2. So refractive index is a measure of the ratio of speed in both media, which is also known as the ratio measurement of the sine of the angle of incidence the sine of the angle of refraction, and also equal to the wavelength in medium 1 of that wave to a wavelength in medium 2, because we have already seen that the wave speed will change as the wave crosses the boundary interface between both media, and the angle the wave makes with the normal will change from incident angle to angle of what? Refraction, and the wavelength too will change. So let's see the relation. It's a simple definition. The refractive index is defined, therefore, as the speed of wave in medium 1, the ratio of the speed of the wave in medium 1 to that of the speed of the wave in medium 2. So if we note this by symbol, we can now say V1 represents speed in medium 1 over V2 speed in medium 2. So the refractive index of medium 1 with respect to medium 2 is wave. So we see that 1, 2, V over 1, V over 2. So with respect of medium 1 to medium 2. If the order is reversed, such that we have the refractive index of medium 2 with respect to medium 1, we shall have the numbers here reversed as 2 to 1, a ratio of speed in medium 2 to speed in medium 1. That will also change for the wavelength too. Lambda 2 will be up and that one will be down. So this chain of equations would also continue here if we wish to comprise. And for water wave traveling for deep region, from shallow water to deep water, speed of wave from deep to shallow water, we shall have speed of wave in deep water. That means V1 over speed of wave in shallow water. If it were to be light, then we'll say the speed of light. For light traveling from air to glass, we can say speed of light in air to speed of light in glass. That will give the refractive index of light with respect to air, glass, medium. So when light travels from air to glass, you can also have that, or from water to air, or water to glass, or light traveling from air to water. All these are waves, mediums where light can travel, and so we can determine the refractive index of these mediums with respect to light, if light is considered as a wave. So that is that for now. Let us see an example on this refractive index for wave. Let's see question. Surface wave traveling in deep water at 50 meters per second are incident at a shallow water boundary. If the angle of incidence and refraction are 45 degrees and 30 degrees respectively, calculate the speed of the wave in shallow water. Solution: the refractive index is n equal to sine I, n over sine r. Speed in deep water, speed in shallow water. I is equal to 45 degrees, R is equal to 30 degrees, V2 is unknown, V1 is known. So if we substitute in their respective position, so I have sine 45 degrees for sine I, that's I is 45, R sine 30, 15 V2 for the speed of wave in shallow water. So with this arrangement, let's do the calculation. Since this part and this part they are okay, and everything sum up to the refractive index between shallow water and deep water, then the refractive index of deep water with respect to shallow water, n, we just leave n instead of writing 1 or 2, just n. The refractive index between deep water and shallow water is therefore sine 45 degrees and over sine 30 degrees in this question, and equal to 15 meters per second, the speed over the speed in shallow water. So this is the speed in deep water. So if we cross multiply these two ratios, leaving out for this n, taking these two parts, we shall have V2 sine 45 times 15 sine 30, and then we substitute the values, and that will give us 0.707 for 45 and 0.5 for sine. and then we divide both sides by the values. So divide or sine 45 degrees. That will say 15 times 0.5. This one represents sine 30. 0.5 is representing sine 30, and this one is representing sine 45. That means 0.7071. And in the end, we arrive at a very good number, 10.01 meters, as the speed of the wave in shallow water. Diffraction of wave is the fourth property of wave. When a wave travels from one region and the wave meets a barrier in its path, if the barrier has an arrow opening or slit, as you can see this opening, the wave will bend around the barrier. So refraction simply means therefore the bending of a wave when it encounters a barrier in its path. Now take note, the wave will go through this opening. This process we say that the wave spreads or flare into the other space or region. The flaring of a wave has to do with the wave front and the wavelength. If the wavelength of the wave is smaller than the opening, no diffraction will happen. But in this very example, you can see that the wave flares well. That means the plane wave front you are seeing right now is traveling from left to right. Look at the arrow. As it goes or bends through the barrier opening, it becomes spherical wave front. That means there's a change in the wave front. This change in the wave front means that the wave has been diffracted, and therefore for this to happen, it means that the wavelength of the wave is by far bigger or greater than the opening, the length of the opening. So if the length of the opening is smaller than the wavelength of the wave, diffraction will happen. But if this opening is quite bigger than the wavelength of the wave, then the wave will just go undiffracted. So this plane wave will still appear as plane wave front in this other region, and therefore we say that there is no diffraction. So diffraction. So we see that diffraction is the bending of a wave when it encounters a barrier in its path. So we also say diffraction is the flaring of a wave. So the waves of the plane wave front, as you can see, flare into the other region or spread out. But you must bear in mind that for this to happen, the condition is that the opening of the slit, the opening or the slit must have a gap or distance shorter than the wavelength of the advancing wave front. Please take note of that. And also note that if the wavelength of the advancing wave is actually smaller than the opening, no diffraction will occur. I repeat, the slit opening must be smaller than the wavelength of the wave for diffraction phenomenon to arise, to ever happen. So we must bear that. So to cap this section up, diffraction simply is the bending of a wave when it around the barrier in its path. When the wave encounters the barrier, diffraction happens basically with the wavelength bigger than the opening. So we say diffraction happens with a wave front bending around barriers in the path of the advancing or traveling wave. So that's that. So I repeat the definition. Diffraction is the bending of a wave when it encounters a barrier in its path, or the flaring of a wave when it encounters a barrier in its path. So that is the definition. And take note, when this happens, spherical wavefront becomes what? Plane wavefront, or plane wavefront becomes spherical wavefront. Interference of wave involves two traveling waves. When they combine, wave A and wave B, they combine. Interference is the superposition of two waves. So superposition of two waves means two waves coming together at some point, they combine. So that's superposition. So interference is a special case of superposition of waves. And interference, the two waves, they must be traveling in the same direction in this type of superposition of wave. And the wave combines in a manner that the resultant wave will either be bigger than the original waves or smaller, or perhaps even disappear. When it disappears or by far smaller, we say that the waves combine destructively, as in the case right now. You can see the resultant wave C formed from A and B is having amplitude smaller than the amplitudes of A and B respectively. So this type of the combination or superposition of wave is called a destructive interference. So basically there are two types: constructive interference and destructive interference. So take note of this. Therefore, we turn our attention to the diagram involving. Here we have the same waves A and B. This time they combine in the constructive manner such that the amplitude of C is bigger than the amplitude of A and B respectively. So here the waves combine constructively. So we must note, for constructive interference to happen, the two waves must combine such in manner that the crest of one wave is exactly in phase with the crest of the second wave. That means the crest of wave A falls exactly in the crest of wave B. So the two waves combine constructively. That implies that the trough of A will fall or match correctly with the trough of B. That means the two troughs are exactly in the same position. When this happens, we say that the waves combine constructively, that is fully constructive interference. We can also have intermediate interference where the wave does not combine fully. It's not fully destructive, it's not fully constructive. Intermediate. Now, for constructive interference to happen, the condition is that, as I said it before, the peak of one wave will fall on the peak of the other wave. Alright, and then also the waves must be traveling such that one wavefront has a zero phase angle with respect to the other one, or that means there is no phase difference between them, or one wavefront has even multiples of phase angle, such as 2 pi, 4 pi, 6 pi. That is the phase difference of 360 degrees between, or multiples of 360. That's 2 pi, 4 pi, 6 pi, 8 pi will be the phase difference between the two traveling waves for this phenomenon of interference to occur. So I recap: number one, for interference to happen constructively, the trough of one wave will correspond with the trough of the other wave. They will combine. Then, when they combine, and therefore we can also say the phase difference between them is zero, or even multiples of pi. That means even multiples of one's angle of one circle, that's 2 pi. So if it's not even multiple, any other one we have will not give us fully constructive interference. Now, if the trough of the other wave B correspond with the crest of wave A instead of trough or crest. Then the two waves will cancel out as well. We saw in the previous diagram. When this happens, we say that the wave is what? The wave interferes disruptive. As you can see here, this is the previous diagram which describes destructive interference, because the trough of one is almost falling on the crest of the other one, so they combine destructively. But when they combine constructively, it reverses the case. And here, the wavelength of one wave is an half-odd integer multiples of pi. That means the phase shift between them is either multiples of 90, odd multiples of 180 degrees, so that we can have 180, we can have 270, we can have the next one 420, and all of that. That would be the phase angle between the two waves. But we don't say angles in degrees. Here we refer to odd half multiples of pi. So please take note of that. Odd half multiples of pi will be the phase angle between the two waves for them to interfere destructively. And for constructive interference, as we have seen before, here for the waves to interfere destructively, the two waves must have their trough and crest cancelling out. So the trough of one wave will sit on the crest of the other one. I repeat, the trough of one wave will superimpose the trough of the other one. The crest will superimpose the trough. So opposite trough to crest, they cancel out. Or the waves must have a wave shift or phase difference of half odd multiples of pi. That means angles that are odd numbers and multiples of pi. Then that wave will interfere destructively. Like, for example, we say add half odd multiples like 270, 420, and so forth. When the phase angle between the two waves happen in that manner, then the two waves will cancel out. Like 270 is about 3 pi over 2. 5 pi, the next one will be 5 pi over 2. Pi over 2, all these are odd half multiples of pi. Pi over 2, that's 90. 3 pi over 2 that's 270. When that means the phase angle between the wave is just 180 or multiples of 180 degrees. And so the waves, what happens? They cancel out. That's destructive interference. So the two conditions, I repeat, trough to crest of one wave, they must merge and add half odd multiples of pi. We give us that result for destructive interference. Constructive interference, we have said before, is even multiples of pi, like 2 pi, 4 pi, not 3 pi, no. 2 pi, 4 pi, 6 pi will give us constructive interference. That is the phase angle, phase shift between the two waves. Or perhaps no phase shift at all, it could just be zero. The phase angle is zero, so the two waves completely correctly match themselves. And then they combine to give us a stronger resultant wave, as you can see, bigger amplitude. So for constructive interference, the amplitude of resultant C is usually bigger than the respective amplitude of the two waves. While for destructive, as we saw the other time, the amplitude is smaller than the amplitude of the two waves. The last concept. Here comes this concept. Polarization is a property of light peculiar to transverse waves alone. Now, this this wave property rather is for transverse wave as told, and we can see a source of wave incoherent in different waveform from the source. They are planes of vibration. The waves are vibrating in different planes from the same source. So what happens? We want to cause the wave to be in one plane. So we need a polarizer to do that. So polarization is production of wave whose vibration is in only one plane or vibrates in one plane. So to do that, we need materials called polaroids or polarizers. Now, with the help of the polarizer, we can make these waves of different vibration to become wave of one vibration of wave in one plane. In this material called a polarizer, we have a dark opening. This actually being an opening. This opening allows wave parallel to its axis or plane to go through, and any other wave that is not exactly parallel to this opening is blocked out, and as a result cannot go through. So therefore, with the help of the polarizer, screening will happen, and the wave therefore produced after the screening is a polarized wave. Polarization is a very important property of all electromagnetic waves, especially light waves. It has a very great application there. So if you ask what is polarization, you should be able to tell that polarization is the production of waves whose vibrations are in one plane of vibration, just one plane. So far we have discussed the properties of wave in subsequent study. We will also review some of the work we have done here. Some calculations are not done, like calculation involving displacement of a wave or the wave equation, and other things that need to be here will be presented in a more packaged form, such that the viewer will have options of various questions being answered for problems in wave, such as theory and solved examples or solved problems. So I believe this section must have impacted positively on us. Please do well to like this video. See you next time.